Hey everyone, today we will be going over how you can remove tokens from a sentence piece tokenizer within Hugging Face, and then how you can get rid of the corresponding embeddings in the model weights and still have the model work properly. So why would you want to do something like this? If you're working with a massively multilingual model, something like XLM Roberta, it has 250,000 tokens and is trained on like 100 or so languages. You're probably not going to be using the tokens for all of those languages. And so what you can do is get rid of the tokens for the languages that you aren't using. And then you can save some space because the whole model, the base size model, is about 1.1 gigabytes. And the word embedding matrix is 700 megabytes. So 7/10 or so, 70% of the model is that word embedding matrix. And so if you get rid of the unnecessary tokens, you can save some space. You can potentially help speed up the model a little bit during training or inference. And if you're using something like Donut, which is a generative model, it was trained on Chinese, Korean, Japanese, and English. You don't have to worry about it potentially generating any languages that you don't want it to. So this should be rather simple, rather quick, but I hope you find it useful. All right, so here we are in a notebook, and here are all of the steps that we're going to do. So as a rough outline, we'll load the old tokenizer, we'll save it locally. That will save a sentence piece model file. We'll open up that and we'll modify it, save it back to a new sentence piece model file. And once we have that new sentence piece model file, we can load that into a tokenizer. We'll need to do a few extra steps to make sure all the special additional tokens are in there, and then we can start working with the word embeddings. And then from there, we can test it out, and it should all work properly. So part one, loading in the old tokenizer. Very familiar to probably many of you. We're just going to use the auto tokenizer with Donut. So we're going to pull that in from the hub. And then we're going to save it locally into something called old tokenizer. And what I've also done is print out the length of the tokenizer, which shows how many tokens are in there. So this one has about 57,500. It's an XLM Roberta tokenizer. So once we have that saved, we can then pull the sentence piece model file from it. And so to do that, we can do something like this. So that loads the protobuf file, and there's a very convenient function within transformers that does that. One thing you may notice is that this 57520 is a little bit different than this. The reason is that there's some additional tokens within this that are added after the sentence piece model is added. So the way it works is that it loads the sentence piece model file, and then the people who made the tokenizer added additional special tokens. So those won't actually be in this file here, but it'll be fine. We can cover that later. Okay, so the next part is removing unwanted tokens. And so again, Donut was trained on Chinese, Japanese, English, and Korean. And so if we look in the tokenizer at some of the entries, we'll see that we have a lot of different values, even an emoji. And so a lot of these are going to get removed. And I wrote a very basic rule for determining what should be kept and what should be removed. So I'm going to loop through every piece in the sentence piece model file. And each piece corresponds with a token. And so I'm going to remove this, which indicates that there's a space in front of the token. So this token has a space in front of it. And you might have another token that doesn't have this in front of it, but I just want to ignore this because I'm more focused on this. And so I'm going to check if all the remaining characters are ASCII. And so there's a built-in string function, and so it's going to check if all the characters within that string are ASCII. And ASCII means that it's going to be like A to Z, uppercase, lowercase. It's going to do basic punctuation, numbers 0 through 9. All of that. So it's just very basic way of eliminating all of these other languages. And so if it does match this, we're going to add it to the kept pieces. And so if we look at what was kept, we can go look at the first 10, and we can see that it is indeed a bunch of plain English terms. All right, so what we're going to do now is loop through all of the tokens, and we're going to check if it's in one of the tokens we want to keep. If it is, we'll just move on to the next one. If it's not, we're going to pop it from the list. And so this modification in place is what's necessary to modify the model. So I'll run that. And after it's running, I can check how many pieces there are now. So we're down to 27,500. So nearly, how much was it? 57. So yeah, basically 30,000 tokens removed. Very nice. And what we want to do now is add a new token into the tokenizer. And the reason is, for Donut, it doesn't have the token for 1. And this token doesn't have anything in front of it. So it actually does have a token for 1 if there's a space in front of it. You can tokenize things like 10 or 1.1. But there's certain scenarios where it will turn 1 into an unknown. So to help you understand what I mean by that is that if I just tokenize the phrase greater than 1, I can see that this is unknown. So I printed out what the unknown token ID is, and so whenever the tokenizer doesn't understand a token, it's going to turn it into unknown. And so whenever you see a 3, that means the unknown token is there. So a more robust example would be a longer phrase that has a bunch of 1s in various scenarios. So 10.1, a parentheses in 1, A1, 10, 1, 11. And so when I run this, you can see that I'm aligning all of the IDs and tokens. And so here, this one is unknown, this one's unknown, this one's unknown. These last 3, these are all fine. But depending on what you're working with, you probably want to be able to handle a 1 that might have something coming before it. And so to do that, we are going to first check for the piece that has the _1 in front of it. And the reason is we want to know what score it has. And we want to know what score it has because the way this sentence piece unigram model works is that this token with the higher score is the one that's going to get into the actual tokenized phrase. So this is overly simplified, but basically if I have this new token and I give it a score of -10, that means that when the model, the tokenizer model, sees something like this right here will get tokenized into the _1 and not just the new nothing in front of it 1. And the reason is, like, the model's already built up a good representation for that old one, so we might as well keep using that. And only when it needs to, like situations like this or like this or like this, that's when we want to add the new one. So that's why our score is a little bit lower than this one. So here we go. We copied a piece, we modified the token, we modified the score, and then we extended that sentence piece model file. So again, we have to work in place because it's a protobuf model. Okay. So we can save this new model file and we can load it into this should probably go over here. So we save the file and now we can load it into the actual XLM Roberta tokenizer. But this isn't quite correct, so we can compare the lengths now. So 27,513, 57,525, and actually if we come over here m.pieces. Oops. We may notice that this is one higher than it was before, and that's because we added the tokens. Here it is, 27.510, 27.511, okay? But now it's 27.513, and the reason is when you load it into the tokenizer, it'll actually add some tokens. And that's fine. We actually need to do that ourselves. And so if we look at the old tokenizer, let's see, additional special tokens. We can see that it added these, and you won't actually find these in the new tokenizer. And so what we're going to do is say new tokenizer.add special tokens. We can add all those tokens in. It says, okay, you added 2 new tokens. Great. And then it actually can't, at this point, it can't handle special tokens properly. So one of the special tokens is this. And if I take the new tokenizer and I say, hey, please tokenize this special token, it'll break it up into multiple tokens instead of just tokenizing all at once. So the weird, quirky way of getting around that is just adding the special tokens, even though it looks like it already has. So if I do special tokens map, it looks like those tokens are already in there, but if we add it again, then that'll actually make it so that it works. So if I come back and run it now, we can see that it'll tokenize it into a single token. So that's all working just fine. Once again, we can do a comparison of the lengths of the tokenizers, and we can see that since we've been adding in a few tokens, we're now up to 515 instead of 513. So the 2 that were added were these ones right here. These ones, the special tokens that were already in the vocabulary, don't count to this because it was like they're already added, but you just have to do this so that they're actually handled properly. All right, so let's make sure we save the new tokenizer, reload it, and make sure that it all works properly. Whoops, I forgot this. Okay, so now the new tokenizer that we are loading will tokenize special characters correctly. At this point, we can move on to the word embedding matrix. Okay, I put together a very basic way of understanding what's going on when you're modifying the word embedding. And so if, say we have a token apple, when you pass the string to the tokenizer, it's going to change it to an integer, an ID representation that is the index within the word embedding matrix. And so when you index into that matrix, you get the embedding representation for that word. And this embedding is ultimately what's going to be fed into the model. And so each of these squares represents some number. And in reality, it'll have, hundreds of dimensions rather than the, what do I have here? Eight dimensions or so. And so imagine this is your word embedding matrix. Each of these rows represents a different token. So I'm only showing 28 rows, but in reality, you'll have tens of thousands. And say, all these red ones are the ones you want to get rid of. And so you can delete those. But the issue is that when you smush it down and have your new embedding matrix, all these IDs don't match up with the old ones. And so if you had, something at index 10, for example, well, 10 actually corresponds with 8 now because 2 were removed before it. And so what you want to do is create this mapping of the old values to the new values so that you can just index the old ones, ignoring all the ones that are gone, and you can create the new matrix. And so this mapping is what we'll focus on next. Okay, so going to step 1, creating a mapping of the old IDs to new IDs. The way we'll do this is by loading in the vocab for the old one, and vocab is the key. It's a dictionary, and the keys are the token, the values are the ID. And so what we'll do is I'll sort all of the new vocabulary because this isn't necessarily in the right order. And so we'll look up the ID of the old one using the token that's in coming from the sorted new mapping. And so what this is essentially a list, and at position I, it'll give you the ID, the old position, the old index in the old embedding matrix. So the new embedding I will have the value at embedding J of the old one, if that makes sense. And I'm not going all the way to the end because the new token we added doesn't have a corresponding embedding, so we have to do something special for that. Okay, so running that. And then because I went to the end, I can show you that the token for number 1 is very close to the end. And these ones actually do have embedding, so we'll have to manage those, but this one doesn't, so we'll do something special. All right, so at this point, we need to actually pull in some weights from the model. And so we're going to use vision encoder decoder with the donut-based model. And the old embeddings can be gotten by doing this. It's going to print out this long message from bits and bytes. Doesn't matter. And if I run it again, then it won't have that message. And so if I look at embed indexes, you can see that it's just a long list of numbers. And so it's going to index in, and the new embeddings will be in this order. And remember, that order is the sorted new mapping. So most of these are the same, but then it'll skip a few, and so it's ignoring the ones that we don't need. Great. All right, because we added that number 1 as a as a token, we have to create an embedding representation for it, and I will just be using the most similar one so that it has somewhat close to the maybe a good representation. So in the old mapping, I will look up what ID this token is, and then I'll find that embedding. We have to do some shape manipulation, but we add in, so we find the embedding for that token 1, and then for those remaining 4 or remaining 3 these 3 others, these do have token representations. So we're just going to look those up, and then we're going to stack them all together. So the new ones with the new embedding for number 1, and then all of the remaining embeddings. And so when I do that, I now have an embedding matrix that's the same shape as or has the same number of rows as there are tokens in the vocabulary. Great. So one other useful thing you can do while you're modifying this is making the embeddings a good multiple. And so if you're working on GPUs or even TPUs, these devices, they work better when their shapes are multiples of 16. Sometimes having it be a multiple of 64 or 128 is important if you're working with really big models or on certain types of hardware. I just set it to 16. It turns out that if you do this, it actually is also a multiple of 64. Let's see. Right, so 27,520 divided by 64. Okay, so it is a multiple of 64. That's convenient. You can look at this link. It's to Andre Karpathy. He was talking about how when he's doing Nano GPT and he changed the size of the embedding matrix, it made a very noticeable speed up. Cool. So we modified the size of the embedding matrix, and what this is doing is it's putting a bunch of empty embeddings into the matrix that they'll never get used because there aren't tokens that exist for it. And so it does take up a tiny extra bit of space, but the speed up benefits are more than worth it. All right, so we've created this new embedding matrix. We just have to put it back into the model now. And so we're going to load it in by doing this. We're going to just assign it into the embedding tokens. We do have to update the configuration in that decoder because the vocabulary size is different now. And so If we take the shape of it, the first dimension, that's the number of rows. And so doing this will save the new model with the new embeddings. All right, next step, we want to make sure that the embeddings are correct. And so we'll have the same phrase, hello there, passed to the old tokenizer, passed to the new tokenizer. And we can see that the IDs don't match because the new tokenizer, had a bunch of tokens removed. But as long as the correct IDs go to the correct embeddings, because these are the exact same model, the embeddings should be the same. So what we can do is we can say, okay, let's look in the old embeddings for each of these IDs. And then we'll have a 5 by the hidden dimension matrix or tensor for the old embeddings, and likewise with the new embeddings, and then we'll check that they're all equal. And so if we did it right, it should say it is true, all of these embeddings are correct. So different IDs, but still same embeddings. And then we can add the rest of the image processor bits of information into the local file so that it's all convenient, and when we call from pre-trained, it's all together. And so if we look in the file, that's the old one. We have the added tokens, we have configuration, we have the model file, tokenizer file, but we also have the preprocessor config. So if you're doing a full training, you can just reference this donut base ASCII for the donut processor for the whole model, and it's all contained nicely. All right, and so now we want to make sure that the token for the new number 1 works, right? So before we were getting unknown, and now we shouldn't get any unknowns. And so we're going to do the same test as before. We're going to tokenize it, and we can see that we are now producing this 27511, this new token for the number 1. We're no longer having any unknown tokens. All right, so now that we've been through all of that, let's actually put it all together and see that it does in fact work. And so here we're gonna, this is a markdown cell. Let me change that to a Python cell. Okay, so this is the old one. We're loading it from the hub. We only need 2 things, a processor and the model. And then if there is a GPU, move it to that device. If not, just keep it on CPU. Okay, so we have the model and processor. What we're going to do now is load in an image, and Hugging Face has these small data sets that you can pull in. And so I'm going to do that and just use a random image from it. I'm using the synth-dog task, and so all it's supposed to do is just generate the text that it sees in the image. And so I need the decoder input ID for this task prompt. And then at that point, we're ready to pass it to the model, and the model can generate some text, and hopefully it makes sense. And so what is this image of? It's some advertisement, has a lot of text. I don't think this is actually similar to what the synth-dog task was like, but it's fine. So we need to get the pixel value, so we pass the image to the processor, and then to the model, the generate function, we need to pass those image pixels, and then the input IDs, a few other parameters, and off it goes. And so it says, love delightfully soft skin, get India's first, and then something, something, something. So what it's looking at is this region on the right over here. It didn't, like I said, I don't think this is very similar to the task that is trained on, so it's understandable that it's not printing out or generating the text for a lot of this, but it actually is reading this part correctly. So this is the old model, and it says wall time 1.98 seconds. This timing magic function isn't great. So if I run it again, it's down to 600, 573, 579. Okay. So let's try it with the new model now. And so this one was saved locally at donut base ASCII, so we can load it in practically the exact same way. The decoder input ID will be a different ID than before. That's fine. And we're going to call the generate function in exactly the same way. And so it says, love delightfully soft skin, get India's first, and it's basically the same text. And so I can copy this, move it down here. It's basically the exact same text that's being generated, which is what's supposed to happen. Because it's the same model, it hasn't been modified at all, apart from removing things. But the nice thing about this is that it is, you can do this before or after training, and so it's very convenient in that regard. So if I run this a few more times, just to get a sense of how long it takes, right? 530, so it is going, marginally faster than before. So if you do something like this, you could potentially get a little bit of speed ups. So I did a couple runs and I'm getting basically the exact same scores. And so here on the top left chart, I'm showing the edit distance. And so this is for using Donut to understand receipts. And so I don't know if you can see it that well, but the red and purple are the new model. The blue and orange are the old model. And so it's roughly about the same score over time. And is the purple model is just barely faster. So in the same amount of time, it does a few more steps than the other older models, but other than that, they're performing basically exactly the same. One last thing I'd like to add is that you could actually, instead of removing tokens, removing embeddings, another way to prevent the model from generating tokens you don't want it to generate is by using this bad words IDs argument within generate. And so what I did, I used GPT-4 to tell me what are all the code points for Japanese characters, and so it created this function. And so to get all the tokens that are considered Japanese, I can loop through the vocabulary, and if this comes back true, that means it is Japanese, and so I print the first 10 tokens that it identified, and indeed it does look like Japanese. And so I have this long list of 13,000 tokens that are considered Japanese. And so if I want to ignore all of these, I have to create a list of lists. And so that's what I'm doing here. And then I am passing that to the model in the bad words IDs argument. And so one of the lists is already the unknown token ID. And so we're adding in those other ones. So we have, like 12,000, 13,000 of these that are being added. But when I did this, it did seem to add a little bit of time to the inference time. And so it's a much easier way of preventing these tokens from being generated, but it can slow things down a little bit. So 579, and then if I use the modified model, 412, and this isn't exact, but relative, it does show that it is slower to do this. I think I also ran it without, this is the original model without doing as many bad words IDs. So here, 464, that's the original one using bad words IDs, 579, and then the modified one, 412. So it is faster if you remove things, but it does take a little bit of effort. I forgot to mention that this is only good for sentence piece models that use unigram. And so some of the other models that you could do are listed on the sentence piece section in the Transformers documentation. And so the ones down here, so Albert, XLNet, Marion, and T5. So this also works for XLM Roberta, as well as Donut, which is using the XLM Roberta tokenizer. I think dberta also uses this as well, but for things like roberta or llama, this approach does not work. All right, so that brings us to the end of the video. I hope you found it useful. If there are any questions, feel free to leave a comment down below. I'll try and make more videos that are helpful like this in the near future. So if you did like it, feel free to subscribe, and more content will be coming in the near future. What I'm showing you now is the final model that's uploaded to Hugging Face. So if you do want to use this model, you can just use this. I also included the code of how to remove tokens from it. So there's a notebook here that shows walks through all the steps that I did today. And so the model here is indeed the one that had all the embeddings removed. The tokenizer here has all the embeddings removed, but also has the number 1 added to it as well. So yeah, hope you liked it, and I'll see you in the next one.